Excellent. Howdy. Okay. We need to start this chapter 12. Hopefully your exams went okay. So yeah, I'm apologize for the rain. I've waited all day. So it's now early morning. Still gotta take a sick day. Hopefully be back on Thursday. But let's get this 12 started. Okay. Kinetics. We talked a little bit about an intro to this, and that we're really looking at graphing the change in concentration versus time and seeing how that change occurs. And so, what I'm really wanting to drive home to is this chapter is about being able to measure those rates. Here's our one from book. So I'm going to measure those rates in terms of lines, and this chapter is really all about lines. So I want to just refresh our memory here of this y equals mx plus b. And so we're going to be playing with this a lot. And so we talked about the fact that this pen is terrible. And we also talked about the fact that the rate is some rate constant times the concentration of whatever we're looking at. Remember, this is molarity. Moles is solute over liter solution. And it's to some power. And that power there, we can't initially tell what that is. And that's kind of the hard part. That was always the part that drove me nuts as a student. Well, okay, I get that they're proportional, that if you change this concentration, it changes the rate. Typically speaking, you increase this, it makes it go faster. K is just a proportionality constant. We see this so much in analytical chemistry. This A always bugged me, all right, because you can't look at the equation and predict it. You can't do things like you could with an equilibrium constant. And so it caused me all kinds of stress. So if A is that little a, if that's 0, then there's no dependence on this concentration, that the rate's just equal to some constant. It just increases, right? If A is equal to 1, then the rate would be depend on that concentration. So if you double the concentration, the rate would double. If you, all right, so this is kind of a direct relationship. Okay, so you double this concentration, you double the rate. Okay, and then we might also then look at if A is 2, it'd be second order. So if I double the rate or double the concentration, then I can, then instead of doubling the rate, we'll have 4 times the rate. All right. So, because it's going to be squared. So we want to be careful about this, but it drove me nuts. Okay, and then they do some weird stuff, and so stuff like if we're looking at the reactants, then they define it as rate. So this is for generally our products, but reactants, because that we talked about that slope being negative, it's going down. So for reactants, they say, you can't see that, but rate equals negative K of A. All right. And so these are the kind of things that we need to look at. And one of the first things that we really got to do is take a look over at this helpful table that they gave us. This is like the best table. So I'm looking at this table, and it's got, so it's 12.6, if I can read that right. So it's got the summary of the kinetics. And so here's our rate law. So if it's 0 order, it has no dependence on the concentration of our product A. So if it's first order, it depends on it. If it's second order, it's going to have that squared. So you take that concentration and you square it. All right, so easy enough. Okay. So then they give us these integrated rate laws. And so you might look at these integrated rate laws and say, man, they're kind of crazy. Well, these are actually pretty easy to plug in. We need to figure out, remember, so let's keep in mind A is the molarity of whatever A is. Okay. And then when they put this 0 down here, they want initial. In other words, when time is 0, molarity. So that's not too hard. If they tell us that initial, then and so if we, all this integrated rate law is doing then is it allows us, if we want to know the concentration at any given time, that if we know the rate constant and at that time and how much we started with, we could solve for that. But this, so you can use that. They'll have problems where you just plug them into here, no problem. So first order, it's got this ln, makes life a little more difficult. But let's go back and look at our equation here then. So when it's 0 order, we got this concentration of A equals negative K T plus concentration of A initial. All right. Now this is the same, remember, as y equals mx plus b. And so all this is really telling us, and it's plotted out in here, and it tells me that if the y is my concentration of A, and then my x will be my time, right? Remember, this is time. It's usually in seconds. And then b is my initial, and so it's where we cross then so this is our y-intercept, right? But that's where it's the time is equal to 0. So that's all that is. Okay, so this, you start with more, it's gonna take a little bit longer to get down to that. Not too difficult. So that's 0 order. So this one, all we're gonna do then, so then the slope of this graph would be equal to our negative k. All right, that's our m. And so it tells us that in this graph, it tells us here, and it tells us that we're going to plot A versus T. And we should get a straight line. Okay. So as long as we match it to that line, we get a straight line, we'll get that relationship. Now that even goes ahead and it goes into the half-life here. So this is how much time it takes for half of this reaction to have taken place. So it's to have lost half of the starting material. And so then we go to first order. And so when I look at first order, it says that it's the ln of A. Well, that's our y equals negative k T plus ln of concentration of A 0. Y equals mx plus b. So again, my slope here is the negative k, because we're going to be looking at the starting materials. And so this is, it's got a dependence then on A. So this is, if I just graph the A versus T, typically you're going to have this slope down and it won't be a linear line. And so what you have to actually do then is graph this ln. And so our y then is ln of that concentration of A. Well, if I have the concentration of A at different times, then I could find this. I could make this graph real easy, where my x would be my time, and then I just have to know my initial stuff over here. So this is not too bad, but what we can do here then, and so when I do the second order, it's got 1 over the concentration of A will be, now notice here that the slope is a positive k. That has to do with that having been squared. All right. And so here I'm going to be graphing this 1 over this concentration versus time. And what this really does for us is allow us to use this table and look at graphs and be able to tell what kind of interaction it is. So there's 2 ways that we define our rate laws. And so it really comes down to, are we looking at changing, are we going to change the concentration relative to the other concentrations? All right. And so if we're doing that, then we usually say this is the differential. And that'll be our differential rate law. And so there, all we really look at is what happened. Did I double? Did it have no effect? So, and then the other kind is these integrated rate laws. And the way we are going to work those is this is going to be change in our one of the concentrations. So that's why they use this A. And we're going to graph this versus time. But we're not just going to look at this and say, oh, is it a straight? Because when I was a student, we kind of learned, okay, you're going to either get a straight line or you're going to get some kind of curve or you're going to get some weird, more different curve. We're not, the problem is when you graph these on your calculator, those things are hard to see. So what we're going to actually do is graph all 3, and we're going to look for the straight line. Okay. And so we should see a straight line when we graph one of these relations. So we'll play with that. We'll come back and play with that. So let's look at some of this data for changing the concentration. And the book goes through and they do a whole bunch of math, but really you don't need, you can do the math. I don't care, so you want to find the slope. Remember, and it's rise over run. In other words, you're going to take your concentration or change in concentration. So your change in concentration minus. So this will be R2 and R1 over time 2 minus time 1. And typically they are looking at the initial rate. In other words, when T is just 0 plus, incrementally small number. So it's just right after 0. So it's not technically time equals 0, but it's just right. I mean, initial, as soon as that reaction goes. But as soon as you put the stuff in, boom, that's time 0, it started. Okay. And so if we measure that initial rate, so if we're plugging in at time equals 0, and we're looking at these concentrations, we can get that slope of our line. And so when we get this curve and we're doing our rise over run, we're actually getting the slope of the tangent line, all right? And so when we do that rise over run, we were doing some of this in class, that calculation is not super difficult, really pretty easy. And we can get that, though, all nice and summarized. What they usually do is they do a series of reactions. So here's A plus B goes to C. And so let's change. They're going to measure the initial rate. All right. And they're going to compare it to if they started off with a certain amount of A versus starting off with a certain amount of B. And they want to see what effect does that have on the rate. Now we could do this and they give us a whole bunch of data, but this is usually going to be summarized over here. And so let's say they did 0.03. This is an example out of one of these out of the book. All right. So here's my initial rate. The first reaction, it had a rate of 0.03 per seconds. And then this, here's my 0.1. 0.2 was my molarity here. So the first reaction, they took A and they had 0.1 molar and they got this speed. And they had B, had 0.2 molar. All right. And then what they did, this next reaction, so when they give you these tables, here's what we might see. And you have to learn to read these tables to see what's important. So here's what's important. In this, so I'll label these. So this is 1 and 2 and 3. So in reaction 2, what did they change? Well, the concentration of B stayed the same. And typically you don't pick 1 and 1 because it, if you have any kind of multiplication or squaring things, it becomes a little more difficult. So what we can tell is that when they changed the rate of, they changed A, they doubled that concentration, right? So they doubled the concentration. So between 1 to 2, they doubled concentration of A naught. All right. So they doubled what they started with. They put twice as much in, and it went twice as fast. And so we doubled the rate. Okay. And that's all we can tell from. And then if we look at we could go from 1 to 3, but notice I don't want to do that because they doubled that again, and they also changed the concentration of B. So what I want to look at then would be 2 and 3. Because here in 2, I've got 0.2 and 0.2. These two, they kept that the same between these two trials. And so this would literally be, the instructions would be, you're going to monitor this, the rate of this reaction. Maybe you're looking at how much C is being produced. And you're going to do one reaction set with certain concentrations, you'll do another one, and it'll tell you to have different. And so you might have said, man, why do we got to do all this? This is all they're doing. And so they changed this concentration. So they increased this concentration. That's the only change they made. Now they didn't quite double. They only went up by 50%. But they increased this initial concentration to 0. And now if this rate had changed, I would need to get the ratio of how much it changed versus how much they increased it. So if it went up, they increased it by 50%, and it went up by 50%, it would be first order. If they increased it by 50% and it went up, then here's where life gets a little more difficult. So then if it's got anything other than linear, then, or being a direct relationship, they went up more, you can assume it's second order. We're not going to hit you with third order, at least in class. All right, so we increased that. But what happened was there was no change in the rate. So let me get my big picture up here for you. So, okay, here's all I'm looking at then. All right, I've got, so we changed this rate here, and we changed the concentration, it changed the rate. We doubled this. I doubled this concentration, it doubled the rate. Over here, I increased this concentration relative to 2, right? And I kept this one, the A, the same, but the rate had no change. It was still that 0.06. So what does this tell me is relative to A, so for A, for A, this is a 1. It doubled, so that's a 1. And then relative to B, it's a 0. Okay? Now, when I write out my rate laws for this, then, and they're going to ask us what these rate laws look like. And so we might say something like rate equals negative K concentration of A to the A times B to the B. Well, now that's a 0. Remember, anything 0 power is 1. So then the rate will just be negative K of A, and it's to the 1 power. Ignore my hole in my board there. And we don't have the B doesn't factor in, doesn't affect the rate. Okay, so that's how we handle these tables where they've changed these concentrations. And so that's our differential. All right, they're not too bad. You may have to plug in some numbers and get the differences in the rates, but typically think in terms of did they double it, and they're pretty good at when you design these experiments. You typically double, or you make some. This I was surprised to see this 0.3. I would have gone to 0.4 so that I can say, hey, this doubled and that doubled, or this doubled and that's quadruple. But that's okay. That's okay. So then what does it look like when we use an integrated rate law? So let's look at the example they like to use in this book. So they're using N2O5, and they're telling us it breaks down into NO2 plus O2. And instead of looking at the relationships of these, they're just looking at my N2O5 versus time. And so they give us this table, and it looks something like N2O5 concentration versus time. And so 0.1 time at 0. So that's how much I started with. That's your initial. So if we wanted to plug this into our rate law, that would be sub-0. And 0.0707, I'm just going to fill these in. And you can start to see a pattern here. And after a while, so this is at 50, and 100 and 200, and they did 300 and 400. All right. Now, after a while, these you kind of learn to look at the data, and you get a pretty good feeling of how these work. But we don't even have to go through all that. So we're looking for this to equal y equals mx plus b. So we're coming over to our fancy table over here, and we come over here, and this is telling us what we need to plot. And so we're going to make a list for these. So let's focus in on our calculator. So here's my calculator, and I'm going to go ahead and set up to plot these. So let's see. So I'm going to turn it on, and I'm going to go ahead and hit this stat, and it gives me a bunch of lists. And okay, right up to the front so I can see. Okay, and so yeah, let's edit the list. And so let's see, stat, clear list, and I want to clear second L1. And there may be a faster way of doing this. And then do this and second L2. I'm just going to clear out my previous list. All right, stat, edit. I'm going to come over here to L1. And this one, I want to go ahead and put my time. All right, so remember we're doing y equals mx plus b. So my time is here. And that needs to be my x. So I'm going to go ahead and put my time in. So my numbers for my time are 0. And then let's see, I can hit enter, and 50 is tougher to do with a mouse. Let's see, and 100. I haven't even tried to see if I can use the number keys, so they're way up there. 200, 300, 400. So there's my things there. And now the L2, I'm going to do my concentration. So I'm going to do 0.1, 0.0707. And then we did 0.05 and 0.025, 0.0125. And you start to see that pattern there, 0.00625. So see how they're decreasing. And so now I'm going to come over. And instead of typing all these in and doing this math, what I'm looking at, remember, is this graph, this stuff. So what I've just done is my concentration of A. Next one, I need to do ln of A. And you could sit here and make a table that says ln of A, but we don't want to do it that way. That's going to take way too long on the test. So I'm coming over here, and I'm going to go up, and you guys should know how to do this from lab. And so now I'm going to do this, and I'm going to say ln of L2. And it'll fill it in for me. And then I'm coming over here, and I need to do, looking at my stuff, 1 over A. So I'm just going to do 1 divided by, and this was L2. And it filled those in. So I've got my nice graph, easy enough. And I could graph these and try and plot them, but what I'm going to do then is I'm going to come up here, second, stat plot. And so I've got my plots. Let's see. I want, so I got plot 1 on and plot 2 is off. I'd like to have, I'm going to go ahead and do these little lines. Makes life a little easier. So let's, plot 2, enter. And, oh, let's do these little fun lines. Yeah, that'll work. And so it's still on off. Okay. And then I'm going to go up, and I can just edit them without going anywhere. So I'll hit enter for plot 3. I want it to look like this little line too, sure. I don't care which one you use. All right, so I've got plot 2. Now, if I put them all on, you can't really see anything. So let's go ahead and try that. And so when I go over here and graph this, I get this a line with no reference points, no nothing, right? So, boy, that doesn't help me. You can really see. Well, that's so we're gonna zoom. So hit zoom, and I'm gonna just hit 9, but it's down here. You can see it. Zoom stat. That's what we want. And now it shows them. There's still not a whole lot going on for us to tell. So, so let's go to the stat plot. And I'm going to come back through here, and I'm going to turn this one off. And I'm going to turn this one off. And I'm going to just look at these now when I go to my graph. And I'm going to go ahead and make sure I'm zoomed correctly. So zoom 9. And now I see that does not look, and I'm going to write down my list here. So we had T versus concentration of our N2O5, and then we had T versus our ln of that concentration, and then T versus 1 over that concentration. And so this first one, man, that does not look very straight at all. Okay, so now I'm going to come over here, and I'm just going to change my plot up. And so just hit enter. I'm going to turn that one to off. And I'm going to turn plot 2 to on. And I go to my graph. And Hang on. Second step plot. Off. Everything should be off. So you can turn all plats off, all plats on. So okay, let's turn everything off. All right, second step plot. We just want this one on. There we go. And now I can go to my graph. And it doesn't look super straight either. Oh man. All right. And then now it's kind of trying to connect the lines. So okay. So it does look a lot like the previous one. So it has me wondering if I've got something wrong. Let's double check things. And then I'm gonna come up here to plot 3 and turn that one to on. And now let's try graph. And again, it doesn't look very good. So let's go back and turn. Maybe I've got this set on the wrong setting. So let's just look at my pretty graphs here. And then we'll turn that one to on. And then we'll turn this back. Let's see. Okay. Great. Now you can see this curve definitely there. So when I'm at zoom 9. Oh, you know what? I know what it is. Ah. Oh, silly that day. All right. All right. Maybe you've got it. You're probably yelling at me. J, you've got L1 versus L2, and L2. Why they're the same? So, oh man. So this one needs to come. I need to come down here, and this didn't need to be L2. Second, that needed to be L3, and then I'm gonna come up here to plot 3, and that needs to be L1 versus L4. And now when I turn them all on, we can see something. Well, I was wondering why I was only seeing that one's on. Why? This the problem is I've got all this set up on my calculators, and just all right. So zoom 9. Well, we got stuff down here and stuff up there, and so it's really hard to see what's going on. Even on when I do these kind of things on the color one. All right. Oh man, let's see. Whatever I got going on here. And so even on these, where it's got color, still almost impossible to see. So I got it hooked up to my computer and went through some wonkiness trying to get that. Excuse me. All right, so let's turn some of these off. So we're gonna go back, and we know one is that funky curve, so we're gonna turn it off, and then we'll come over here to plot 3, and we'll turn it off. Now I can go to my graph. We see a whole lot of nothing. It looks like a fairly straight line, but we better zoom. So zoom 9. Now, oh man, that looks a lot more straight, right? Definitely more straight than the other one. So we might call that one pretty good. So I like that one. So then let's look at the other one. So we're going to turn number 2 off. You got to kind of keep up with which ones are which. All right, so this one versus L3, that was versus our LN. So I'm gonna just come over here and I'm gonna label this. This was L2, and this is L3, and this was L4, just to keep track of which ones are which. And this takes a lot less time after you've practiced, right? And so we got that one off, and I want to look at plot 3. Put that on. Hit my graph. We see nothing, so zoom 9. And then, okay, I can clearly see that curves upwards, right? So we have one that curved down this way, one that was fairly straight and one that curved upwards. What we're looking for is that nice straight line. Easy enough, right? That's what I thought. We've got, you got a curve that comes this way, a curve that goes that way, and a curve that goes that way, right? So 0 first and second for this data. Now the problem here is our problem. We get these data points. They're not as, this was, the book picked these. I mean, this is clear cut. They're not as easy as this most of the time. And so what we really got to do is, when you've only got a few of these data points, let's say I'm down here, I'm down in this area where it's hard to tell that this is curving up. How do I even get that figured out? Well, what I'm going to do is I'm going to come down here to my stats, and I can go on. I'm going to go to calc. Sorry. I'm going to come down here to this linear reg. Lin reg. What? So it's the linear regression. AX plus B. So that's one we want. There's another one if you keep going and they do it the wrong way. So we want AX plus B. And we want L1 versus L2. And we will calculate that. And it'll tell me y equals AX plus B. A is my slope. And that, hey, there's my, remember this is negative K. So my K is actually that, 2.2. All right, so that's fine. And this would be my initial concentration according to that. But that doesn't tell me if that's a straight line. So when I come back and I do another calculation, and I come down here and I make this second L3, and I come down here and calculate, and now I see a different slope. But it's hard to tell. This is great. This will give me the slope. I can use that in my calculations. But what it doesn't tell me is how straight is that line. And it's actually doing that calculation. This is the place to see this. And so it turns out that there's a mode your calculator needs to be set in. So I'm going to come down here in mode. Don't Google how to do this. It'll have you going through the catalog, and it's a lot of scrolling. But when I never pay attention to this next because I never use it, right? So you come down here, you got math print, you got classic. People get stuck in math print all the time with automatic fractions. Man, good luck with that. So I'm coming down here to the stat diagnostics. I'm going to turn that to on. And you're going to turn that on, and you're going to leave it on. So now I'm going to second quit. I'm going to actually hit up and do this linear regulation of that same one, L1 and L3. Now it gives me a lot more data. It gives me the R squared and the R. Now these, just think of them as, if they're equal to 1, it's a perfect fit. So they're descriptions of how far, and it's two different statistical analysis tools, but it's how close it is to a straight line. So if it's 1, it's absolutely, boy, that's pretty darn close. All right. And so then when I come back and I do stat calculate, and I'm going to go back and look at that L2, and we should see that it is in no way as close. So you can see the R value is quite a bit smaller. And then when I come over to, so what I would do is I'd write this one down, and I'd write the other one plus minus, I don't care, right? But so that's why they tip was square it here. But it gets rid of that plus minus. And then if I come back and I do my calculate, or so R again looks pretty close here, but that 0.88 is really far. So it's definitely not 1. And so if you get 3 graphs that look very similar, you're going to need these R squared values. And so I just look at the R. You can look at R, you can look at R squared. It doesn't really matter. You're gonna get the same kind of idea. R squared just kind of magnifies the differences. But if you just write them down, the one that's closest to 1, right? Usually it ends up being R squared. It's the biggest one, the closest one. That's your winning. And so what is this telling me? Well, this told me over here when I'm looking at my data that this was my linear line, was this L3. And when I come back and I look at my chart over here, this tells, hey, if it's this, it's first order. And that tells me this is first order. And if it's first order, then the rate is, and it says it'll be K A. And it's a 1 there. You can just leave that. And then you could do all kinds of calculations and stuff. But usually we're just going to ask, is it first order? Or what would be the rate law? Okay. So these are the calculations we got to do. So we'll be giving you a bunch of these. And you've got to figure out which rate law is it. And the worst thing you can do on those, I mean, sometimes Dr. Milligan is even crazy nice. He'll come in and he'll label this, and I'm going to scoot this time 1 over here, and he'll say, here's L1, and do this one in L2. And then he comes over and he said, I'm going to jot it down, and he'll do, here's L1, and it's your time, and you go through. And here's L2, and it's your concentration. And here's L3, and he wants you to do Ln of that concentration. And here's L4, and it's 1 over that concentration. And you, even if he gives you a table here, you don't fill out that table. He'll give you da 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 here and da da da. For those, you type those in. Don't manually calculate these. Go through, let the calculator do it. I mean, that's why we paid so much for these things. Hey, this one on my screen over here is not too bad. So when you do these lists, remember you can go up and you change this formula. Okay. So when I change this formula, I can change that list by saying it's this Ln of L2. All right, so don't forget to get those. Easy enough. Make sure the key take home is make sure you do this diagnostics mode. So mode, come down to stat diagnostics, and you want those on. Now, I don't even know what stat wizard is. I got the clock right. That's because it's on my computer. One of mine's a 2001. Man, I don't even know when I bought that calculator. I'm guessing sometime before 2001. So that'll get us through a large part of this discussion. And so as we do this chapter, I'll spend more time on it. The next big thing we got to worry about is mechanisms. And really that comes down into breaking down these reactions into the subparts of these reactions. And one of the terms that the book leaves off, but they use a little bit, is this idea of they'll have, let's say, okay, so A plus B goes to D. And then, but it's really A plus B goes to C, and then B, I don't know, and C plus E actually go to our D. And we don't know what E. All right. And so when we do a lot of these, we've got these multiple different mechanisms going on. And they'll a lot of times have language in here like slow and fast. And this is one of the great things about rates is we can figure out the rate laws for the slow one And then we might have another mechanism, and somebody else might say, no, that's silly. It's A plus B, and it goes to C, and C actually reacts with B again, and that's what gives me D. And so there's two different, and they say this one is slow, and this one is fast. And we could actually figure out these rate laws by looking at which one's slow, which one's fast. All right. And so it's actually the steps here. And these steps is called the rate determining step, or RDS. And it's whichever one is the slowest. So the slow, when they say slow and fast, they're just telling you which one do we need to worry about the rate law for. And so we could figure out what the rate laws would look like for the different steps, and then we would match it to our data and look at the data. And if the data told me, hey, it had no dependence on E, or hey, it really depended on B, that it shows up, in that rate determining step, then that's going to be really important to us. And so, for instance, if A had no effect on our overall reaction, then I know it's not this first mechanism. Okay. And this is actually one of the things that when we talked about catalysts, and we said, here's our reaction. So you got your starting material, your products, and here's our energy. Usually this is delta H. And so we said let's do an exothermic reaction where we're releasing the releasing the energy, the enthalpy trapped in the bonds. So now that extra energy is released, but this was our energy of activation. Okay. And so if we're trying to do a reaction like this and we want to speed it up, I told you it lowers this. Well, a lot of times the way it lowers that is by changing the mechanism, and it might give us some small one and a slightly larger one, and then it comes down. Where the overall one is still lower, but now it's got multiple steps. And so we'll talk later about what's at the top of these steps and what's at the trough. So the top is where we have two things in the process of banging into each other. And so that's a transition state. Ones you're reading this material. And then in the troughs, we have that. Remember, I said there was like a C or something, right? And that's something that we could maybe collect, and that's an intermediate. We never collect a transition state. It's impossible. It's when they're banging into each other. Okay. And so they're in the process of reacting. The bonds. So we usually think of, okay, the bonds break and then they come here. Well, this is when they're halfway through breaking and halfway through forming. And so they're just kind of, everything's kind of all connected. Half of the bonds are broken and half of. And then other things, you have an intermediate where the bonds break, and then one of the broken pieces runs off, hits something else, and that's what starts the reaction. And so this idea of the mechanisms and a catalyst speeding up a reaction, a lot of times it does so by changing the mechanisms. All right. And so each one of these would have different energy of activation. The bigger energy of activation will be our rate determining step. All right. So we'll worry about a lot of this, but main thing I wanted to show you was your calculator and how to get that going. So we'll stop there, and I'll catch you on the next one. And I'll have to give you a little more details on some of these mechanism stuff, but we'll use a lot of these terms. So, all right. Enjoy your week, and I'll see you hopefully on Friday.